Hey guys, welcome back. So, I have no patience and I just went ahead and modeled the factory cap. So check this thing out. I'll give you a visual of the cap and I'll show you the real one. And they're actually fairly close. I mean, this isn't a perfect model because at the end of the day I'm not building a factory cap. So I don't actually need to know precisely how it looks. But check this out. So this is the model and I'm fixing to switch to the actual part. That's the part. Alright, so this thing's really close. You can see we tried to get all this little weird notch geometry, the radiuses on these posts coming out. See how the top of the cap, this thing necks down back here? So it's not full width. So we really got all that geometry on there. And it's all within, other than like these radiuses, the actual locations and heights and all are all within a couple thou. So we have a pretty good model of the factory bearing. So what we're probably going to do is to run FEA on this, and I haven't done it yet. I haven't even set up to do it yet, and I'm still thinking about how I'm going to do it, because part of me, so I could sit here and do FEA and be like, oh, well, the computer says this, but one thing I've thought about, and I probably will do FEA, but one thing I've thought about is to actually do real-world testing. The problem is I haven't figured out how I would do it yet, but let's just, let me show you what I'm talking about. Okay, so here's our block. Now, we talked yesterday, when the crank pushes, essentially, if this was a crankshaft, it's going to be pushing up on this bearing, you know? So basically, it's going to come up here and push on that top cap, and that cap's going to bend upward, like this is going to move up. So, one of the questions is, well, how much do these move? And this is probably something we could measure. Essentially, I just need to build something that I can put in here and push on that cap, push upward with. So, possibly, for example, say I built something that was basically a bolt that I could reach in here and put a torque wrench on. Now, I can't exactly do it the way I'm describing, but, you know, just imagine I could put something in here and push upward. And that upward force would bend the cap. Now, what I could do is I could take like a dial indicator, set up an indicator somewhere on the block, like maybe set it over here or wherever, and put an indicator right on the top of that cap and put a known load on it and see how much it bends, or if it bends at all, and if it's measurable. And then after you do that, then you could say put ARP main studs and torque them up and see how they do. You could even try different torques and see if any of that makes a difference. And then lastly, if we build our new cap, we could bolt our new cap on here and we'll perform the same test. And of course the hope would be that the new cap, being stronger and with a higher rigidity, it would deform less than the stock caps with either factory bolts or with ARPs. So we're tempted to do that even if we do FEA. So here's the thing, if we do FEA, that gives us insight before we make the part. So we may want to change something after seeing the FEA, but frankly, the mechanical engineer in me says, make it big, make it beefy, and it'll be stronger and more rigid, and that's about it. So I don't think there's a whole lot of optimization. Really, the only constraints you run into are the actual dimensions of the block. So let me show you what I'm talking about here. I'm going to fire up the light, get a little zoom going on. So see this little notch where the cap sits in? This has a name, I forget what they call this, but basically, when you put the cap in the block, it's actually touching on the sides. That's what locates the cap into the block and keeps it square. So if you take the caps off and you put them back in the block, that's what makes sure they actually go back to the right spot. And that's fine, that's what you want. But you'll notice, after this comes up a little bit, on this side, see how it stays pretty much the same size as the block. And when you come over here, on the other side, you'll see it kind of notches inward. Now I can guess they probably did this so that it's just a small amount that you have to machine to just basically it makes it easier for manufacturing and setting it up. But I mean, it's obvious that, hey, we could have made the cap wider. That would have made it stronger. So it's kind of a missed opportunity. And of course the top of the cap, you can see like over here, it's already necking inward some, and then it really necks in right there. And then, frankly, I don't think this main bearing support plate's doing very much, just because it's sheet metal. So I really don't give that any credit. I mean, I guess we could test it. Well, it'd be hard to test because you got to bolt the pan on and all that. But I kind of doubt that does much. So, all this metal that's taken away from here, I bet you that if this was just solid metal, say this was just like a flat surface from the factory, and it didn't have those bolt holes, I bet you it would have been a stronger part. I bet that's true. So anyway, this is kind of our thoughts on Mazda's design, and now we're going to look at what I came up with. Alright, so this is my design. You'll notice a few things. It's very simple. and it's very beefy. That's really all there is to it. Okay, there's dimensions and tolerances and stress and things like that, but generally speaking, that's about it. So let me show you the comparison of these two components. So on the left we have the cap I designed, and on the right we have the cap Mazda put on the 01 through 05 Miata. As you'll notice, one is a little bit beefier than the other. So let me do an isometric view. Yeah, check that out. I mean, these are like night and day differences. But the crazy thing is, look at this. If I put them side by side, they're the same height. If I do them from the front, the part that actually hooks to the block is the same width. So this will drop in, even though this cap is taller and wider and thicker. Despite all the dimensions that I modified to improve the stiffness and strength of this cap, this will still drop into the factory block. So I got a feeling if we end up building caps, we're going to do a design very similar to this. I mean, look at this top section. How much metal you got, just solid metal. So if you bend the cap, you got to bend all of this metal. That's like a big solid steel beam. Whereas you come over here on the other side, that beam is really cut and notched right up here at the top. So what would happen is this top section is the part that would bow and flex. It would move out of the way. It just doesn't have any stiffness. It doesn't have a lot of strength. Whereas this one just being a big solid beam, it does. Let's look at a top view. You can really get a feel for, the differences. So you can tell on this one on the factory, they really pulled this in toward this whole top section. So really, if you think about the bottom section where it's actually full width, you go from here to here. So let me see what that number is real quick. Okay, so that may be a little hard to read, but that's 0.603 inches. So basically 0.6 inches. That's how much metal we have that's actually full width of the beam, which whatever that is. But anyway, you got about 0.6 inches tall before you get into all this stuff, which really ain't doing much since it's so narrow. Now let's look at the other one. Yep, 1.248, so 1.25 inches. So that is a huge improvement. That's what, double basically? Or real close? 0.6, double 0.6 is 1.2. So it is double. Yeah, so this is double the thickness. But that doesn't mean it's double the stiffness or double the strength. The way beams work, this would be more than double. This would be a huge improvement in stiffness. So I bet you, if we did an FEA analysis, you would probably see this. Yeah, granted, this stuff up here would have added some stiffness, but it would not surprise me if this was double the stiffness of this design. And that's before we changed material. That's assuming that this was, cast whatever the hell this thing's made of. So we know that this will be a better material too. So we're going to see improvements from material, which you would expect with a billet cap, but we're going to attempt, and I expect to have an improvement due to design as well. So when you put the two together, say the material might give you 50% more stiffness and say, 100% more strength. Well, then we're going to also achieve, say, double the stiffness due to the design. So if we got a 50%, go to 1.5, and then you double it, that would be 3. So this might be 3 times stiffer, and it'll be much, much stronger, way more than this, because this beam is so damn thick. So yeah, I expect this would probably end up being about 3 times stiffer overall, and possibly more. But yeah, huge improvement. You can kind of see. Visually, just looks beefy as hell. So what I'm thinking about doing is, I want to build these. I tried to get some quotes, and I haven't really heard back from many people. And the downside is the material has a long lead time. So if I decide to make these, I'm going to be waiting, which kind of sucks. I hate waiting on stuff. And I called my machine shop. I'm waiting to hear back from them. So, man. Anyway, but I do think we're going to end up trying to build these. And if it works, great. And if it doesn't, it's okay. It'll still be fun. But you can tell this new design's fairly simple. So we'd have to figure out the fixturing, how to hold it to do our tool paths. But I think that's what we're going to work on next. See if we can't get that stuff figured out. Anyway, what do you guys think? Y'all like stuff like this? Basically, try to actually build our own engine parts. Starting off with something simple, a main cap. It's just a piece of metal with a couple of holes and a big hole here and profile around the outside. And really the distance from that surface to this surface over here, that's about the only critical one, that 3.841. I measured that earlier. That's what it measures on the block. So we'll adjust this once we build these, because we probably want this to be a press fit in the block, maybe like a thou or so. So we'll see. But that's about the only thing that's super critical, because this bore here is going to get line bored anyway. And if this thing's a few thou taller, it doesn't matter. You're just putting a bolt in a nut, or a stud in a nut. And as long as this is high enough that it won't interfere with the block, we're good to go. So this isn't too, these sides here, if these are slightly out by a couple thou, that's not gonna, as long as it doesn't hit the block and it's got adequate clearance, you're okay. So it's a fairly straightforward part. So I think we can pull this off. The machine limitations may slow down the speed, but I don't think it's going to stop us from building it. It just might slow us down. So anyway, if you guys like to see this kind of stuff, feel free to subscribe and send this to your friends and like the video and that kind of thing. Because I can't believe this, but we're at 299 subscribers. We're about to hit the 300 mark. It's crazy to me. This channel, after I started this channel in probably 2008 or something, I mean, I've had this forever. And as of a couple months ago, I was up to like 142 subscribers. So it's like I would pick up a few every year. And now I've went from 142 to we're fixing to hit 300. So that's awesome. So thank you guys for sticking around, and hope y'all enjoy this, and kind of let me know what you think, because part of this channel, I'm going to be doing stuff I want to do, but also it's kind of to entertain people and show you guys how we do stuff. So if you'd like to see more of the modeling or the FEA or the actual real world testing, measuring stiffness, machining, whatever kind of stuff you guys like to see, just let me know and I'll make sure and keep more of that on the channel. All right, you guys take it easy.